Hello everyone. We'll be covering how to write a minimum cost algorithm. We're going to start with a brute force method, then we're going to improve that and I'll show the pseudocode for that. After that, we'll explain which dynamic programming techniques we did, and finally I'll demonstrate the method I chose pictorially. Starting with the brute force method, we would have a minimum cost definition that would accept a list of prices. I've showed an example of prices there, and we would also need to keep track of position. For the first occurrence or the first iteration, we would start with the highest position, so that would be our end position, we'll say, which would be the length of the list minus 1. We'll start with our base case, and in the base case it would be if we're at the 0th position or the first step, so the first 2 steps. And if we're at the first 2 steps, then we know that we're just going to return that price. Otherwise, we're going to make recursive calls. So we'll do the 2 neighboring positions to the left. And if we were thinking about this as a tree, even though it's a list, we could think of making a call as the left position if we call the one immediately next to it 1 position over, and our right position would be the minimum cost 2 positions over. In our base case, it would look something like this, calling the minimum cost for both of these 2 positions, 7 and 9. Finally, in the case where we are recursing, we would then just return our overall cost, so it'd be prices of our current position, and then the minimum cost of both our left and our right. Now this would be the brute force approach. If we thought about it as a tree, it would break down into every single subproblem. This gives us a recurrence relation of t of n is equal to 2t of n minus 1 plus some constant, which overall gives us an exponential O of 2 to the n. Now we're going to think about improving this. And the approach that I thought was more interesting would accept the prices similarly, and then it would know that the base case and our optimal prices for the first 2 would just be the prices at the first and the second index, as we can't become any more optimal than that. Now, for every step after that, we're going to be finding what the optimal price would be. So we would now iterate over it in the range of all past this. So this would look something like 2 to the total length. Now for this, each time we know that position will be its price, and then we've also already calculated the optimal price for those that come before it. So we're going to say that in our optimal array, that this position J is going to equal prices of J and plus our minimum value from the two immediately preceding, those that we could reach if we stepped 1 or 2 steps back. We'll write that since we're running out of room. Finally, this will have iterated over it and have calculated at each step of our optimal array, we would be able to we would know the optimal value. But since we wanted of the overall prices to reach the end step, we would return the last value of optimal. Now this is quite a bit faster. So this is going to be order of n, or O of n. And this is using bottom-up approach. And at each step we go through, it's calculating the optimal value. And then once we iterate one step further, we already have solved the optimal values for all of the previous, so we can find the optimal value within the 2 steps that will fit for us and give us the best solution. I'm finally going to explain this pictorially and to take a bit more room. We could assume that we have an array, or we have prices of 1, 2, 5, 7, 9, and 3. We would take those first 2 and we would slot those into our array. We already know that the optimal solution for this first step is 1 and the optimal solution for the second step is 2. Now we need to bring down 5. And with 5, we want to find the closest, or the step within 2 steps that's lowest. So we can bring over the 1. And that's going to give us 6. And for the next step, we're also concerned with the previous of 2. Now we're bringing down 7. And again, we'll want to find the minimum, which in this case is 2. So here we'll now have 9, and we'll also be concerned with the 6. Finally, or not finally, we'll bring down 9, and again, we'll be concerned with the optimal, which is 6, or the minimum, which is 6, giving us 15, and we bring the 9. Finally, to come to our optimal solution, we bring down the last value, or the last price, which is 3, and we bring in the minimum value, giving us 12. So now all throughout the list, we have it where we have the optimal value for the 3rd position, 4th position, 5th position, and our last position, ultimately giving us 12. All right, thank you very much.